In 1998, I went to Carnegie Mellon University to study and do some research in artificial intelligence. 2 years after, I started a company in that field, and 2 years ago, I sold it to IBM. Now, I've been in that field of AI, of artificial intelligence, for the past 16 years. Yet, if you asked me 5 years ago, if I thought computers could do what they do today, I would have laughed. I would not believe you. Now, what's so amazing what computers can do today? What's this new dawn of cognitive computing, and how do they do that? Well, let me present to you Watson.
From 1911 to 1917, this romantic Russian composed Etude Tableau for piano. Watson?
Who is Rachmaninoff?
Rachmaninoff is correct, and that adds to your lead. You're at 13,400. Go again.
Don't worry about it. For 1,200.
You just need a little more sun. You don't have this hereditary lack of pigment. Watson?
What is albinism?
Good.
Cambridge for 1,600.
Answer, daily double. What are you going to wager?
I'll wager $6,435.
I won't ask.
Now, Watson may sound a little silly sometimes, but it did go on and win the daily double, did go on and actually beat by a wide margin the best 2 players at Jeopardy in the world, and did earn $1 million for a charity. So the question you may ask is, how does Watson do it? At first sight, you will imagine, okay, Watson must have this huge database of knowledge, and it takes that question and converts it to a language it can understand. It will query that big base of knowledge and then find the answer. Well, actually, it doesn't really work like this. Instead, what Watson does, it works actually based on a lot of very messy knowledge. It gets the information from the internet. How reliable is that, right? It will try to crawl that information, gets all the text, and then from that information, it will generate hypotheses, candidate answers. Not just one, dozens of them. And for each of these candidate answers, it will try to create evidences that that answer is actually the right answer. Next, it will actually learn what's the importance of each evidence. Do they really matter? Does it tell you that this is going to be the right answer to the right question? It will rank all these candidates and basically answer with the first one if its confidence is high enough. Now, this method is more statistical than just based on fixed knowledge. Is not new. It was not invented for Watson. There's actually a long tradition of these kind of techniques, and you have to go back 40 years, again, to another IBM researchers to figure out where that comes from. Now, this is Fred Jelinek. He was an IBM researcher in the 70s, and he decided at some point to tackle the problem of speech recognition. Now, at the time, there was a lot of influence from a big linguist called Noam Chomsky, and everybody who was in that field thought that the way to crack these linguistic problems was to actually look at the language and understand the grammar, etc., etc. Now, Jelinek was not a linguist. He was actually an information theorist. He would deal with signal processing. Now, what he decided to do is to put a team of linguists and engineers together to try to crack that problem. Now, the story goes that one day, one of his linguists quit. And Jelinek was not able to replace it with a linguist, so he actually replaced him with an engineer. Now, to his big surprise, a few weeks later, he realized that the performance of the system actually improved. It was better at speech recognition. Now, he decided in an experiment, he went to see a next linguist and say, hey, why don't you go find a job somewhere else? Now, what happened is that a few weeks later, the performance of the system, improved again. So then, one by one, he talked to all his linguists and convinced them to go find another job somewhere else. And at the end, he had no linguists left, just engineers, and the performance of the system was actually the best of its time. Now, to understand how you can solve a problem like speech recognition just with statistics, let me jump another 20 years later. Now, at the time, it was still the same team, and they decided to address another problem which is a little easier to understand, which was machine translation. Now, you'd imagine if you had to create a system, a computer, that understands language to be able to do machine translation, you would have to understand the grammar, the semantics, the syntax of one language and try to map that to another language. Well, wrong. That's not what they did. Instead, what they use is data. They use what you could call a gigantic Rosetta Stone, a set of translation, examples of translation, gigabytes and gigabytes of translations. And they will just look at it from an information theory standpoint. What they do is look at a few words on one side that you have to translate, and find in this huge corpus what are the most likely translation in these 3 words. Then move that one word and look at the next 3 words and figure out, okay, what are these 3 words most likely to be translated in that big corpus? And by chaining just these little words like this and figure out the most likely path in all these potential paths, you come up with a translation. And once again, at the time, it became the best algorithm to do machine translation. To this day, when you go to systems that do machine translation, they use the models designed by that team. Now, when you put the speech and the translation together, you get something like this.
I'd like to reserve a flight from New York to Beijing tonight at 8:20.
我想订今晚8点20分从纽约到北京的航班。
请讲。
你要订单程票还是往返票？
Would you like to book a one-way or round-trip ticket?
A round-trip ticket returning on the 23rd of August.
一张在8月23号返回的航。
Now, how cool is that? Now imagine, now you could actually look cool without having to fork $1,000 for an iPhone 6, right? Now, you know, the best example of statistical learning is actually our brain. The brain doesn't learn through rules or fixed knowledge. It actually tends to learn by examples and by repetition. Now, in the 50s, you know, people tried to apply, you know, understand what happens in the brain and try to apply it to computers, and they didn't really succeed because the computers were not very powerful. But in the last 5 years, the huge improvement I'm going to show you in a minute actually all came from trying to mimicking what happens in the brain through what we call neural network or deep learning. Let me give you an example of the first task, the first commercial task that was resolved through these artificial neural networks, and explain why they work. So the problem here is that when you send mail, right, you write a zip code on an envelope, and then, you know, the zip code tells the system where to send your letter or where to route it. Now, what if we could do that and recognize the zip code automatically? So there's a team of researchers in the 90s that tried to tackle that problem. And what they found out is that it was much harder than you thought, because when you look at numbers and all the different ways people have to write these numbers, if you try to explain, if you try to write some rules that says, oh, this is a 4, this is a 3, this is a 2, you will always find another person, another way of writing the numbers that would defeat that rule. Instead, they created a system using this neural network that can look at very, very tiny evidences and lots of evidence. Back to what I was saying to you about Watson, the same principle. Find a lot of evidence to decide if something is a 4 or something is a 3. But these evidences are not, they're very subtle. And you can get the network to learn these evidences by training it. And through this, they actually managed to create a system that's used today to route your mail. Now, the beauty of neural networks, right, is that not only they're able, like Watson before, to weigh the different evidences and combine them and make a determination that's very subtle, but they're able even to come up with the evidences. When you have a network like this, and the reason we call it deep is because there are many layers, you feed in the raw information, the image or the sound, and the system will actually learn to extract meaningful attributes automatically out of this. You know, a diagonal line, something that looks like a face, or something that looks like a cat face. The system can learn to extract very advanced features and combine them to make pretty advanced predictions. And what's remarkable about these neural networks is what they have been able to do in the last 5 years. Let me go through a few examples. Now, back to speech recognition. I believe that everybody in this room not only has neural network in their brain, but they actually have them in their pocket. Today, most of the speech recognition system, when you talk to your phone and you try to recognize your voice, actually are based on neural networks developed either by IBM, Google, or Microsoft. This is the state of the art today. Now, speech is not yet there. It made a lot of improvement. It's not yet there. Let me show you some other tasks where computers are getting closer to what we can do. This is a very interesting task. It's about recognizing what's on an image. So ImageNet is a collection of millions and millions of images that have been tagged by people to say, okay, this image is about a container ship. This image is about a leopard or a mushroom or a cherry. Now, the question is, could you get on a computer, when you show it the next image, to determine what's the main topic, what's the main subject on that image? That competition was created in 2010. At the time, the best computer could actually have a 30% error rate. So 1 out of 3 will make a big mistake, okay? Now, the year after, it was 28%. But then people started using this neural net I talked about before, deep learning, and their error rate went down to 15%. The year after, it went down to 10%. And this year, the best team got 6%. Now, that may not tell you much, but a train expert in that task will actually get a 5% error rate. So computers are 1% away from what humans can do. What's remarkable about this is that to go from the 15% to the 6%, people didn't have to invent new algorithms. They didn't have to find new ways of determining what's the difference between a mushroom and a cherry, what's different between a human face and a cat face. They actually threw just more data at it and created much bigger network. It appears that the networks work so well that when you throw more data and when they become bigger, they become more subtle and can make these very tiny determinations. Now, not only computers can be close to human performance, sometimes they can be better. And the next one is really ironical. I'm sure you have seen these things, these CAPTCHA. CAPTCHA were designed so that when you go to a website, the website can determine that you're actually a real human. Now, the irony here is that Google actually bought that company, bought CAPTCHA, but they also have a team that created a system that now can break CAPTCHA better than humans. So what's the point, right? Now, another task, even a little more creepy, that Facebook, that now has access to all your pictures, has determined a system that by feeding a lot of pictures of people, is able to recognize the face of people better than human. Imagine a computer now can recognize your friends better than you. How humiliating that. Now, what's remarkable about all these advances is that they all use kind of this same type of algorithm, these neural networks, that are very similar to how the brain works. Now, our thought right now is that we can actually expand that even more. And I'll show you a couple of things that my team is working on today. What we believe is the next frontier is to apply these neural networks to language. As the previous speaker talked, conversation, language is very, very subtle, lots of subtleties, and it's very hard to try to articulate, to formalize, to create a linguistic that's so deep that can understand all these things, all these subtleties. But we believe that neural networks actually can learn through training to actually identify all these subtleties and understand language as well as human. Now, beyond language, what we can do with a neural network is combine different modality. I told you they can handle speech, they can handle vision, they can handle language. How about we could combine them? Let me give you an example that my team is working on. When you're in a room and there's a lot of noise, lots of people talking, if you talk to someone, actually, you don't just hear what they say, you actually look at their lips moving. And when you can look at their lips, your comprehension of what they say is actually much higher. We're actually able to create a system using neural network today who can not only hear, but also look at the lips of the speaker and have as much gain in comprehension as humans. Now, if you see where I'm going here, is that we are able to create these networks that can understand sound, understand vision, understand faces, understand language, and it starts looking very much like all these modules of the brain. And we believe that we can combine these things, and as combining them, we will get to something that looks very much like human communication. Now, the next question you may have is, okay, so when will we get there? When will a computer, like Hal here on the left, will actually match human performance? Well, a lot of computer scientists have made a fool of themselves by making very big predictions. I'm not going to do that, but I'll give you some facts here. On the left is what we have today. So these networks actually are not that easy to reproduce. So the biggest network we're able to create today have millions of nodes and billions of connections. What happens is that the brain is actually much more powerful than that, actually 100,000 times more powerful. It has 100,000 billion nodes and 100 trillion connections. Now, if you believe in Moore's law, which is still working this day, which is that computing power increases, doubles every 18 months, you get to a number, which is in 25 years, we should be able to match this. Now, does that mean that we'll be actually able to match all human power? I don't know. If you ask me, I would say no. But remember that also 16 years ago, I didn't think we'll be here where we are today. So I think it's a real possibility that soon in our lifetime, we will see computers becoming as powerful as human. But would I bet on it? I don't know. I don't think so. Now, what's sure is that there is this convergence between trying to understand our brains and trying to reproduce through machine learning what they are doing. Now, if you don't believe me that this is, happening, that there's something really tremendous in the making here, just follow the money. Recently, Google actually acquired a company called DeepMind. And it was actually created by this guy, Demis Hassabis, a neuroscientist. And all that company actually done that we can see today is to create a neural network that could play video games. But Google thought it was so good that they spent $300 million on that company without any product, just people. Now, let me finish this presentation with one last thought. on one hand, what's amazing about this is that as we're able to create this system that behave like human, we feel like we are getting close to this holy grail of really understanding how human work and how human cognition works. But on the other hand, the big criticism that these networks and these deep learning techniques I showed you have encountered is that we actually don't quite understand how they work. And remember this little task I showed you about trying to figure out the different images. If I look at a network and figure out, okay, how does that network differentiate a human face from a cat's face, and a cat's face from a plant, and a plant from a stone? There's no way I can look that is going to show me the features. I cannot verbalize it. I cannot rationalize it. And maybe at the end, what it tells us is that this quest we have had for hundreds of years, of linguists trying to formalize language, of psychologists trying to understand, how we behave and formalize it, maybe that quest is a little bit futile in a way, because what is there to understand more than this neural network? Maybe all we are and all it is this really tremendously parallelized, this fantastic, adaptable, changeable, complex neural networks and amazing learning. Thank you.